Question number 1. Determine whether each of the following relation are reflexive, symmetric, and transitive. So in this question, they have given us a relations that we have to find that whether it is a reflexive, symmetric, or a transitive. The first relation which they have given us, the relation R in and set A is equal to 1, 2, 3 till 14, defined as R is equal to x comma y, such that 3x minus y is equal to 0. So they have given a relation set A has from 1 to 14. So the elements which are there is from 1 to 14 in set A, and the relations they have given that x is related to y in such that the equation they have given that 3x minus y is equal to 0. If this condition is satisfied, then only those elements will be, means the order pair should satisfy this 3x minus y is equal to 0. So first we will find all the ordered pairs which are there in this relation. So here we have A is equal to 1, 2, 3 till 13, 14, and our relation is given as x comma y such that 3x minus y is equal to 0. So first we'll find the ordered pairs. First we will simplify this equation, that is nothing but 3x minus y is equal to 0. So nothing but 3x is equal to y. We'll take the values of the x and we'll see if x is 1. So if x is 1, then you will get 3. So if x is 1, then 3 into 1 is equal to y. So 3 ones are 3. So y will be my 3. So the first ordered pair will be 1 comma 3. The next is if x is 2. So if x is 2, then we have to see the y value, that is 2. 3 into 2, so it is 6. So y value is 6. So the next ordered pair will 2 comma 6. Then if x is 3, so 3 into 3, that is 9 is y. So the second one is 3 comma 9. The fourth, if x is 4, then 3 into 4 is equal to 12. So y is nothing but 4 comma 12. Now if we take x is equal to 5, so 3 into 5 y, where it is 15. So we cannot take 15 because here the set A has only till 4. So set has till 14. 15 is not belonging in this set. So we cannot take 15 has, means 5 comma 15 ordered pair cannot be taken because 15 is not there. So our ordered pairs are nothing but 1 comma 3, 2 comma 6, 3 comma 9 and 4 comma 12 are our ordered pairs. So we can write relation is equal to, we'll write it in the roster form, that is 1 comma 3, 2 comma 6 and 3 comma 9 and 4 comma 12. So this is our relation. Now we have to prove that it is a reflexive, symmetric and transitive. So first we will see for the reflexive. So we'll see for the reflexive. The condition for the reflexive is if a relation is reflexive, if we tell the relation as in reflexive, that is A comma A should belongs to R for all the values of A belonging to set A. So here A comma A means what? There should be 1 comma 1. So here we have 1 to 14 elements. So 1 to 14 elements, here we should have 1 comma 1 because A comma A is mirror image. You should have 1 comma 1, 2 comma 3, 3 comma 4. But we does not have 1 comma 1 in the relation. So 1 comma 1 does not belongs to R. So since there is no such element, so there is no such pair So R is not a reflexive. So R is not a reflexive. The next we have to check for the symmetric. So if a relation, so if relation is a symmetric, if we tell if relation is symmetric, if A comma B belongs to R, then B comma A also should belongs to R. So here A comma B is there in the R, means there should be a B comma A also in the R. So if we take the first example, first ordered pair, that is 1 comma 3 belongs to R, then this implies that 3 comma 1 should also belongs to R. So 3 comma 1 should belongs to R here, but we don't have 3 comma 1. So 3 comma 1 does not belongs to R. So R is not a symmetric. So R is not a symmetric. Okay. Now we have to prove for the transitive. So for transitive, so you tell if A comma B belongs to R and B comma C belongs to R, that means that then so A comma C should also belongs to R. So here if A comma B belongs to R and B comma C belongs to R, then A comma C should also belongs to R. So if we take one example, that is 1 comma 3. So we know that 1 comma 3 belongs to R. Then 2 comma, then 3 comma 9. So 3 comma 9 also belongs to R. This implies that 1 comma 9 should belongs to R. But here we have 1 comma 3. Okay, and 3 comma 9. So 1 comma 3, 3 comma 9. But 1 comma 9 is not there in our relation. So 1 comma 9 does not belongs to R. So R is not a transitive. So this relation is given that it does not satisfy reflexive, symmetric, nor a transitive. The second one is the relation R is a set of n of natural numbers defined as R is equal to x comma y, that is that such that y is equal to x plus 5 and x is less than 4. So here they have given a set of natural numbers. Natural numbers are nothing but 1, 2, 3, 4, 5 till infinity, and they have given us a relation telling that x is related to y in such that y is equal to x plus 5 and x should be less than 4. So the relation here is given that R is x comma y such that y is equal to x plus 5 and x is less than 4. So they have given us this. So here they have told us that x is less than 4. So less than 4 means the x value will be 1, 2 and 3. Because it is less than 4, we can have only the value 1, 2 and 3. And it is given us as a natural number. So we have to find the value of the x, value of the y. So y, the first if x is 1, if x is done, then y is nothing but 1 plus 5. So we get it as 6. That is 1 comma 6. If x is 2, then y is 2 plus 5. That is 7. 1 comma 7. And x is 3. Then y is equal to 3 plus 5 is 8. 1 comma, this is 2 comma 7 and this is 2 comma 8. So we have a 3 ordered pairs, that is 1 comma 3, 2 comma 7 and 3 comma 8. So our if we write in the roster form, that is 1 comma 6, 2 comma 7 and 3 comma 8. So we have 1 comma 3, 2 comma 7 and 3 comma 8. 3 comma 8 is our ordered pair. So we have to find whether it is a reflexive, symmetric or a transitive. The first we'll see for the reflexive condition. So reflexive condition, if a relation is said to be a reflexive. So if we are telling that relation is a reflexive, where A comma A should belongs to R, for every A belongs to set set N. So it belongs to set N. So we should have A comma A. A comma A means we should have 1 comma 1, 2 comma 2 and 3 comma 3. But here we does not have any such pair like 1 comma 1, then 2 comma 2 and 3 comma 3. Now all these three does not belongs to R. So all these three does not belongs to R. So since there is no pair, since there is no pair, so R is not a reflexive. So R is not a reflexive. Now next we have to find for the symmetric. So symmetric, if a relation is said to be symmetric, if A comma B belongs to R, then B comma A should also belongs to R. So if you are telling if A comma B belongs to R, then B comma A also should belongs to R. So here if we are taking 1 comma 6, so if we take 1 comma 6, so 1 comma 6 we know that it belongs to R. It is there in the R. This implies that 6 comma 1 also 6 comma 1 should belongs to R, but here we don't have 6 comma 1, so 6 comma 1 does not belongs to R. So R is not a symmetric. So R is not a symmetric. Okay, the next we have to check for the transitive. See, if A comma B belongs to R and B comma C belongs to R, then A comma C should also belongs to R. So here if A comma B belongs to R and B comma C belongs to the R, then A comma C should also belongs to R. But here you can see that we have 1 comma 6, but 6 comma number is not there. Any number, there is no number such that if we take a 2 comma 7, then there should be a 7 comma some number. But here we does not have any such pair at all. So since there is no pair, so since there is no pair, so no pair, so R is not a transitive. So R is not a transitive. So here this relation is not a reflexive, symmetric or nor a transitive. Third question, relation R in the set A 1, 2, 3, 4, 5, 6 has R is x comma y. Y is divided by x. So here they have given us a set that is A is equal to 1, 2, 3, 4, 5 and 6. So we have a set that is 1, 2, 3, 4, 5 and the relation is given that where x and y are related in such that y is divides, so y divides by x. So y is divided by divides by x. So we have to find all the ordered pairs where y is divided by the x, that is r is equal to. So the first one is, so we know that the first, if we take x value as 1, so if we take x value as 1, 1 can divide with all the numbers. So like 1 can divide by 1 itself, 2, 3, 4, 5, 6, all the numbers are divides by 1. So we can write 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 5. So for 1, every number will be, all the numbers will be divide by 1. So next, if it is for 2, then 2 is divided by 2. Then 2 can divide, 4 can be divides by 2, and next is 6 can be divided by 2. So we have 2 comma 2, 2 comma 4, and 2 comma 6. The next is 3. If we take x value as a 3, then we have only 3, 6 can divide with 3. So we have 3 comma 6. Only 3 comma 6 and as well as 3 comma 3. So 3 comma 3 number can divide by itself, and 3 comma 6. The next, if we are taking the 4, so 4 can divide by itself. Okay, then any other numbers, no, it can't divide any other number because we have till only 6. 6 cannot be divided. Again the same with 5, and again with 6, 6 comma 6. So these are the ordered pairs which can be divided, means y can divide by x. Now we have to check for the reflexive. So for the reflexive, so the condition is if a relation is said to be a reflexive. So if a relation is a reflexive, so if a relation is a reflexive, a comma a should belongs to R. So for all the a values, a comma a should belong in the relation. So here we can see we have 1 comma 1, then we have 2 comma 2, then 3 comma 3, then 4 comma 4, and 5 comma 5, and 6 comma 6. So we have 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4, 5 comma 5, and 6 comma 6. So all the elements, so whatever we have from 1 to 6, we have 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4, 5 comma 5, and 6 comma 6 belongs to R. So for all the elements, the A is present in R. Therefore R is a reflexive. So we have told that this relation is a reflexive. Now we have to check for the symmetric. So we have to check for the symmetric. So if we tell it is a symmetric, then A comma B should belongs to R. Then B comma A also should belongs to R. So B comma A also should be there in the relation R. So if we are taking 1 comma 2 belongs to R. This implies that 2 comma 1 also should belongs to R. So here do we have 2 comma 1? No, we don't have 2 comma 1. So 2 comma 1 does not belongs to R. So 2 comma 1 is not there in the R. So therefore R is not symmetric. So R is not our symmetric. Next, we have to check for the transitive. So transitive, what do we tell if a relation is a transitive? If A comma B belongs to R and B comma C belongs to R, then A comma C should belongs to R. So here we have A comma B. So we will take any such example which have following. See, if we take 1 comma 4 belongs to R and 4 comma 4 belongs to R, this should implies that 1 comma 4 should belongs to R. So here we have 1 comma 4, then 4 comma 4, then it implies that 1 comma 4 also belongs to R. So we have all the elements. So this 1 comma 4 is also belonging to R. So R is a transitive. So we have proved that it is reflexive, transitive, but not a symmetric. The fourth one is the relation R in the set Z of all integers defined as R is equal to x comma y, where x minus y is an integer. So here they have given a set of integers. So integers means all the negative numbers, 0 and the positive whole numbers will be in the set of Z. So that is Z is equal to -3, -2, -1, 0, 1, 2, and 3. So this will be the set of Z integers. So Z is an integer. So we will have all the integers. Then they have given us a relation where R is x comma y such that x minus y is an integer. So they have told that x minus y should be an integer. So we have to prove for the reflexive, symmetric and transitive. So the first we will check for the reflexive. So reflexive, okay. So here if a relation is said to be a reflexive, so if a relation is said to be a reflexive, if a comma a belongs to R for all the a belongs to integer z. So here they have told we have to check for a comma a belongs to R. So we know that any number subtracted, for an example, if we take 1 comma 1, so 1 comma 1 is nothing but what is it? 1 minus 1 is nothing but a 0. So we have x minus y. So x is 1 and y is 1 is obviously 0. Any number you take, a number which subtracts by itself is 0. So this is an integer where 0 belongs to an integer. Therefore R is a reflexive. So here we proved that R is a reflexive. The next we have to check for the symmetric. So symmetric, if we tell that relation is a symmetric, if a comma b belongs to R, then b comma a should also belongs to R. So here we have to check that a comma b belongs to R means b comma a also should belongs to R. So if we take and see here, that is x minus y and y minus x are integers. So we have to check that x minus y and r minus y both are integers. So if we take a value as 1 and y has 2, that is 1 minus 2. So 1 minus 2 is minus 1. If we take 2 minus 1 is also 1. So both are integers. So 1 minus 2 also is there, 2 minus 1 also. For any value if you take, you should get an integer value only. So here we can see it is belongs to integer only. So both are integer. So R is a symmetry. So R is a symmetric. Next we will check for the transitive. So we are going to check for the transitive. So in transitive, if a comma b belongs to R and b comma c belongs to R, then a comma c should also belongs to R. So here if we have a comma b and b comma c belongs to R, then a comma c also should belongs to R. So if we take, so that is that where x comma y and y comma z are integers. So we know that x comma y and y comma r is an integer. Then we have to prove that this implies that I have to tell that x minus z is also a integer. So is also an integer I have to take. So if we can this v x comma minus y, we can rewrite it as x comma minus y plus y is equal to z. You can see that x and x cancel. I can write x minus z as x comma minus y plus y is an also is an integer. So we can write this x comma minus y has like this also. So if we take any simple example like x is 1 and y is something minus 2 and z is minus 4. So we know that x is what? X is 1, x minus y is, so x minus y is what? 1 minus of minus 2. So we get 3. It is an integer. Okay, the same thing if it is y minus z. So y minus z is what? Y is minus 2, then minus of minus 4. So how much will be my answer? It will be plus 2 is an integer. Then x minus of the z. So x minus z is 1 is, this is what? X is 1 minus of minus 4. So we get it as 5. So we can see that all are integers. So R is a transitive. So R is a transitive. So here we have proved that this relation is reflexive, symmetric and transitive also. So the fifth question is the relation R in the set A of a human being in and town at a particular time given by. So they have given a set with of A has a human beings are there in the town. So human beings in a town at a particular time. Under that we have totally 5 questions, where first one is R is x comma y, where x and y works at the same place. So two person are working at the same place. We have to prove that whether it is a reflexive, symmetric or a transitive. So the first thing is we will check for the reflexive. So if it is a reflexive, so if we tell that if a relation is reflexive, so if we tell if a relation is reflexive, that is a comma a should belongs to R for every a belongs to set A. So here for all the values of a comma a should belongs to R. So if we take here a comma a, that is here we have taken that x, right? So x comma x means x and x means what? The same person. So same person himself, if we take himself, he is working in the same place. So x and x can work at the same place. So same person is working at the same place. So if we're taking the same person himself is working at the same place. So x comma x belongs to R. So therefore R is a reflexive. So reflexive. So next we have to check for the symmetric. So symmetric, if we tell that it is a symmetric, that is a comma b belongs to R, then b comma a should also belongs to R. So if we are taking x and y, so if x and y work at the same place. So if we are taking, so and x and y are working at the same place. If a person, x person and y person is working in the same place, then if you take ulta is also the same thing. Y and x person is also working at the same place. Therefore, even y and x works at the same place. So they both are working at the same place. So therefore, R is a symmetric. So it is a symmetric. Okay. Next, we have to check for the transitive. So if we tell a relation is a transitive where a comma b belongs to R and b comma c belongs to R, that implies that a comma c should also belongs to R. So here if I'm thinking that x and y, so x and y work at the same place and y and Z works at the same place. So here x and y is working at the same place, and the same way y and z is also working at the same place. This means that even x and z is also working because y is common. See, y is working, x and y is working same place, then y and z is working same place. Then it means that x and z is also working at the same place. So it means that x comma z is also working at the same place. So this is therefore we tell this is R is a transitive. So in this question we have proved that it is reflexive, symmetric and transitive. Question number B, where R is equal to x comma y such that x and y lives in the same locality. So here in this question they have given that x and y are living in the same locality. We have to check for the reflexive, symmetric and transitive. The first is they have given that x and y. So for the reflexive, where x comma x should belongs to R for every x belongs to A. Here, if you are taking a same person to himself only, so but the same person, X person is living with himself in the same locality. So this is a reflexive where X and X are the same person who is living in the same locality. So x and x are the same person who is living in the same locality. So this is a reflexive. So therefore R is a reflexive. So it is proved that R is a reflexive. Next we have to check for the symmetric. So in the symmetric we tell that if x comma y belongs to R, then y comma x also should belongs to R. Here, if an X person and Y person are living in the same locality, then Y and X also should live in the same locality. So we know that X and Y lives in same locality. So we know that x and y are living in the same locality. If we change the order, if we tell the first y and the later x, it's one and the same. Both will be living in the same localities. Like y, x lives same locality. So it doesn't make any difference. Both will be living in the same locality. So it is proved that it is reflexive. So x, y belongs to R. Even y and x also belongs to R. So R is a Therefore, R is a symmetric. So, R is a symmetric. Next, we have to check for the transitive. So, in transitive, if x, y belongs to R and y, z belongs to R, then x, z should belongs to R. So here x and y are living in the same locality. So we'll write as we know x and y are living in same locality and y and z are also lives in same locality. So if x, y is living and y and z will be living, it means that even x and z are also, so it means that x and z is also living in the same locality. X and z also lives in the same locality. So we can tell x and z also lives in the same locality. So transitive is proved. So R is a transitive. So in this question, we have proved that it is reflexive, symmetric and a transitive. C question, r is equal to x comma y, that such that x is an exactly 7 centimeter taller than y. Here they have given as a x person is exactly 7 centimeter taller than the y. So here we have to check for the reflexive, symmetric and transitive. So the first is for reflexive. So reflexive will tell that if x comma x belongs to R for every x belongs to A. So for every element of x we should have x comma x belongs to R. So here if we are taking an person's x is 7 centimeter taller than himself, it cannot be possible. So if a person x is 1 meter, if a person x is 1 meter, then the same person x cannot be 1.7 meters or 1 meters 7 centimeters. So it is not possible. Himself he cannot be 7 centimeter taller. So here x cannot be taller than himself. So x cannot be taller than himself. So R is not a reflexive. So R is not a reflexive. Now we have to check for the symmetric. So symmetric, what we tell, if x and y belongs to R, then y x should belongs to R. So here we have a person where y is 1 meter tall and x will be 1 meter 7 centimeter taller than the y. So he'll be 7 centimeter taller than the y. If this is an example, if we take y will be what? 1 meter and x will be 1 meter 7 centimeter. So y is 1 meter but x is, if we take ulta wise, but here the y will be 7 centimeters shorter than y, it cannot be taller than y. So reflexive will also not satisfy. So here we'll write x is taller than y, but y is y cannot be taller than x. So because he'll be shorter, he won't be taller at all. So if you take, he'll be the shorter than the x by 7 centimeter because y is shorter, y is exactly 7 centimeter shorter than x. So he'll be, because y will be exactly 7 centimeter shorter than the y. So R is not a symmetric. So it's not a symmetric. Okay. Now we have to check for the transitive. So transitive, if, so what do you tell? If x comma y belongs to R and y comma z belongs to R, then x comma z should also belongs to R. So here it should be also belongs to R. So here if we take as x has 1 meter 7 centimeter and y has 1 meter, then z has So if we take away x has 1 meter 7 centimeter and y has 1 meter and z has 93 centimeters. So here we know that x is greater than, so x is 7 centimeter greater than y and y is 7 centimeter greater than z, it is by 7 centimeter and he will be by 7 centimeter. But x is greater than y by 14 centimeter, because here 1 meter 7 centimeter, if you subtract 93, so you will get 14 centimeter. So it will be 14 centimeter, he'll be x will be taller than the z, so it is not exactly 7 centimeter, so this is not a reflexive. So here we'll write, when x is taller than y and y is taller than z, but x is not 7 centimeter taller than z, because because he is because he is 14 centimeter taller than z. So it should be 7 centimeter. So he is 14 centimeter taller. R is not a transitive. So here we have proved it is not reflexive nor symmetric, but not even a transitive. So D question, R is equal to x comma y such that x is a wife of the y. So here they have given that x is a wife of the y. We have to check for the reflexive, symmetric and transitive. The first we will check for the reflexive. So it is x comma x belongs to R for every x belongs to set A. So here they have told that x is a wife of y. X is a wife of x itself. How can x be a wife of x itself? Like, you imagine your mother. Your mother cannot be a wife of herself itself. So it is not possible. Cannot be wife of x. X cannot be wife of herself only. So R is not a reflexive. So R is not a reflexive. Now we have to check for the symmetric. So in symmetric, if x comma y belongs to R, then y comma x should also belongs to R. You know that x is a wife of y. So x is a wife of y, but y can be a wife of x. No, he is an husband. So he'll become an husband of the x. So they cannot be a wife. X is a wife of y, but y is not a wife of x, because he is husband of the x, so he cannot be a wife, so he is an husband of the x. So R is not a symmetric. So R is not a symmetric. Now we have to check for the transitive. So if x comma y belongs to R and y comma z belongs to R, then x comma y belongs to R. So we have to check for this thing. So here x is a wife of y, y is a wife of x, but here x is a wife of y, but so x is a wife of y, but y cannot be a wife of z. there will be no such pair that Y can be a wife of a Z. Like your mother is a wife of your father. Can your father be a wife of some other person? No, it cannot be. There is no such pair where Y comma Z. There is no such pair at all. There is no such. There is no such pair. So there is no such pair. You cannot have Y comma Z because Y cannot be a wife of a Z. Like your father cannot be a wife of another person. So there is no such pairs. So R is not a transitive. So in this question we have proved that R is not a reflexive, nor a symmetric, not a transitive. Question number E, R is equal to x comma y such that x is a father of a y. Here they have given that x is a father of y. We have to prove for reflexive, symmetric and transitive. The first is we have to check for the reflexive. So in reflexive, x comma x belongs to R for every x belongs to set A. So here x any person can be father of himself. It is not possible. So x is not a father of x. So R is not a reflexive. So R is not a reflexive. Now we have to check for the symmetric. So symmetric is what? X comma y belongs to R, then y comma x should also belongs to R, right? So here if we think as x is a father of y, then y should be a father of x, but it is not possible because your father is the father of your, but you will become a son or a daughter of your father. So it is vice versa is not possible. So x is a father of y, but y is not a father of x. So it cannot be father of x. He'll be a son or a daughter to the x. So R is not a symmetric. So R is not a symmetric. So it is not a symmetric. Next, a transitive. In transitive, x comma y, if we tell a relation is transitive, x comma y belongs to R and y comma z belongs to R, then x comma z should belongs to R. So it should belongs to the R. But here we'll check that if x is a father of y and y is the father of z, okay, but what happens here? X is a father of y. So imagine your grandpa is the father of your father and your father is the father of you. But what will be x? X will be the grandpa of you. So he cannot become a father. He is a grandpa of you. So, but x is not a father of z because he is a grandfather of z. So he'll be the grandfather of the z. R is not a transitive. So in this relation, it is not reflexive, nor symmetric, nor a transitive. Thank you for watching video. Please subscribe.